All right, so the plan for today, we're actually gonna deviate from the course schedule just a little bit. We're gonna start chapter 11 today. And the reason is I don't want to start a whole new chapter one day before the spring break and then have, a week and a half before we come back to the chapter. We are starting into some complex material in chapter 11, so I want to get chapter 11 started today. Uh, do a little more in chapter 11 on Wednesday, and then we'll leave the rest of chapter 10 and probably a little bit more in chapter 11 as a supplement that I'll post later this week. So the quote of the day for today is, it's attributed to Albert Einstein. I think it's always good to be careful whenever something's attributed to somebody famous, because sometimes somebody less famous said it and then people just said that the more famous person said it to make it get a little more popularity. But supposedly he said everything should be made as simple as possible, but no simpler. And I think that's a good thing to shoot for when modeling, when we're dealing with mathematical models of any sort. We don't want to make them too simple to the point where they don't have the I don't know, the complexity needed to model the thing that we're trying to model. But on the other hand, if it's too complicated of a model, maybe it does a decent job of modeling the thing we're trying to model, but maybe it's really hard to understand, really hard to work with. Can we have just as strong of a model, but make it simpler? And kind of where does this apply practically to something like math, outside of obviously mathematical modeling? When we're going through a problem, typically we want to reduce complexity before increasing complexity. For instance, if you're going through an algebraic problem, it's good to, if you're, say, here on the complexity level, you want to decrease complexity, maybe by simplifying some things, maybe doing some combining like terms or simplifying fractions before you increase complexity. And, this kind of a pattern manages the complexity well. We don't want to just increase complexity a whole bunch and then try to make our way down the other side. It's going to be much more difficult to handle. Another example of that is my sister and her family. They lived in Northern Ireland for 5 years and just this past summer moved back to the US. So that was obviously a very complex thing, dealing with finding jobs and schools for the kids and place to live and all of that. If you're, at a life stage where something is very complex, maybe try to reduce all of the complexities outside of what's necessary. Difficulty in general scales non-linearly with complexity. So if something becomes, say, twice as complicated, twice as complex, it's probably much more than twice as difficult to deal with. So, so keep that in mind for both, math problems. When you're trying to solve a problem, can you simplify something? Can you, even if you have a complicated problem that's fundamentally complicated, if you don't know where to get started, can you think of a special case? Can you solve the special case? And maybe that gives you a hint on how to solve the more complicated problem, right? Can we deal with lower complexity before increasing the complexity? And so both in math and in life, I think it's good to manage that complexity. There will be times in your life where complexity is necessarily high, like, having a kid or something like that. And maybe in those times, trying to reduce complexity in other areas to manage the total difficulty is something advisable. Okay, but again, we're going to start on chapter 11, and we're going to see that we're moving into a chapter that is fairly technical and fairly complex, specifically when we get to 11.2 and the rest of chapter 11. But we're going to start with sequences, and this is going to provide the foundation for really our whole discussion of chapter 11. Okay, so what is the idea of a sequence? The idea of a sequence is pretty simple. It's a function whose domain is, and I'll say more or less, kind of roughly speaking, the natural numbers. And the natural numbers, we sometimes refer to that with the symbol kind of like bold N. And those are the numbers 1, 2, 3, and so on, these strictly positive integers. Sometimes you'll hear the term whole numbers roughly used interchangeably with natural numbers. I think often folks say that whole numbers start with 0, 1, 2, 3, and natural numbers start with 1, 2, 3. But a lot of times those two concepts kind of overlap quite a bit. Now, what's the more or less part here? Well, we could have a sequence that starts at, say, 4. It goes like 4, 5, 6, and so on, where the domain starts there. We could even have a sequence that like maybe is just the odd numbers, 1, 3, 5, 7, or the even numbers. We would still say those are sequences because they kind of have the fundamental properties of the natural numbers. What's the fundamental property of, or what are the two fundamental properties of natural numbers? There's a starting number, and then there's a concept of the next number, starting number, and a concept of next or a successor number. So we start with the number 1, and then our successor, what's the next number in the domain? That's 2. What's the next number after 2? It's 3. If we thought of something like the real numbers or even the real interval, say 0 to 1, okay, that has a starting number 0. But like, what's the next number after 0? It's not 1. There's a bunch of numbers in between that. Is it 0.1 or 0.01 or 0.001? There's no idea of a next number in that real number, even that real interval 0 to 1. Or if we thought of the integers overall, it has a concept of next. Each integer has like a next number, -10, the next number is -9, and then -8. But it doesn't really have a starting number. There's no place to start. So it's a function whose domain really satisfies these two characteristics. So there's a starting number, and for each number, there's a next number. There's a successor function that can be applied to it. But typically, we just kind of by default think of using the natural numbers as the domain. So we have some notation. Often we write sequences in curly braces. And often we write, instead of something like f of x, we write a subscript n. And we might want to be explicit and enumerate that n goes from 1 to infinity. So we could say that this is a sequence. So here an takes this domain, the natural numbers, and its range is the real numbers. It does not have to have natural numbers as its output. It can have any real number as the output. So some examples. Say cosine of n equals 1 to infinity would be an example of a sequence. Now, the interesting thing about a sequence is I can kind of enumerate the terms. I can kind of do this a little bit with a real valued function, with a real to real function. I can make a table of values, and I can pick out like sample values, sample inputs and their outputs. But here I can really start listing all of the inputs and outputs below a certain number. So I could also say that this is the sequence cosine of 1. That's the first element. That's when I plug in the first input. This will be my first output. Cosine of 2 will be the next element of the sequence, the second element. Cosine of 3, and so on. So I noticed that a sequence is a list of numbers that's infinitely long. And in particular, they're real numbers, just to be clear. So the inputs are natural numbers, they're positive integers, but the outputs are going to be real numbers. Sometimes we have a sequence that where we can kind of represent the terms nicely in an algebraic format like cosine of n. Sometimes I just list the elements of the sequence. Let's start with 1. And if I list enough to where you kind of see the pattern, maybe that is enough to define the sequence. So we have ones with 1 0 between them, and then 2 zeros, and then 3 zeros, and so on. Or I might have a sequence like this. So this might be another example of a sequence. I mean, trying to figure out an algebraic structure that would give these numbers as the outputs for an input of 1, 2, 3, 4, etc. would be, I think, quite cumbersome to do, but we can list it out and we can see, okay, I understand how this sequence is made. I understand how to get the next element from the current element. There's this, again, concept of next. I can also have examples like the famous Fibonacci series, Fibonacci sequence, jumping ahead to section 11.2. And the Fibonacci sequence does have an explicit algebraic format, but it's kind of, if you looked at it, you think, how does that even relate to it? But we could write it out much more easily. We start with 1, 1 as the first two elements. And then we get the next element by adding the previous two. So 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2, 5. 5 plus 3, 8. 13, 21, and so on. So we actually can do like fn equals, and then some big function of n. I think it has square roots and all kinds of crazy stuff. It's really kind of very interesting that if you look up the function that generates these numbers, that you'd say, how does that function ever generate those numbers? But it does. But this is really cumbersome. I'd rather not go this route. But I do recognize that there is a definitive pattern. I can get the next number by looking at the previous two numbers. So I can define my sequence kind of algebraically like this with an explicit algebraic function. I can define it by just enumerating a bunch of terms. I can also define it recursively. I can say, here's how you find the next element if you already have some elements. What might that look like? Well, the fundamental idea is that the next element is the sum of the previous two. This is a recursion. If any of you have done any computer programming, you might have encountered a recursion before. This is a recursive definition. This says you find the next one based on the previous two. Now, I do have to be careful. What values of n does this apply to? Does this apply to like n equals 1? Well, f1 plus f0, we don't have an f0. So this applies to n bigger than or equal to 2. So f3 equals f2 plus f1. f4 equals f3 plus f2, and so on. That part looks good, but I've only told you how to find f3 and higher. I haven't told you how to find f1 and f2. So in any recursion, we have the recursive bit here, which is, really the kind of part that we mainly focus on. It's the part that does the interesting work, but no less important is the base case. I need to tell you how to find f1 and f2, right? I need fn for n equals 2 and fn minus 1 for n equals 2 to get the thing started, and then it can the recursive case will take off from there. So f1 is 1, setting that one in place. f2 equals 1, setting up that element, and now I have two elements to work with. My recursion will kind of keep chaining them on and keep linking another one to the end forever. So the recursive case is the most interesting probably, but the base case is no less important. And if you've done any proofs by induction, this might have a bit of a similar feel to it. So we have a recursive definition. We can just enumerate a bunch of the elements of the sequence, or we can write out the algebraic definition for generating the terms. The algebraic definition is nice because if I asked you what's the 1/1,000,000th term of the sequence cos of n, it's cos of million. I can tell you right away. What's the 1/1,000,000th term of the Fibonacci sequence? I have to do more or less 1,000,000 calculations to get there, right? I don't have a way to pick that one out. But it is very nice to know how, especially in situations like this one where each element is tied closely to its neighboring elements, it's nice to explicitly write that sometimes, and sometimes can be very helpful. Okay, so that's the idea of a sequence and some of the basic notation and so on. As kind of an aside, if we're not being explicit about the domain, if we just wrote something like sequence an, we would assume the domain is the natural numbers. But again, I could, if I wanted to, I could be interested in a sequence that starts with n equals 5 or something like that. Or I could have like a sub 2n. So, right, I could be dealing with examples where I don't use all of those natural numbers, but I use something that has the same properties, that it has a starting number and each number has a next number for the domain. And again, super important to remember that the outputs, like we see here or here, can be any real number. It's just the inputs that we're restricting. Okay, so we have this kind of interesting structure now. We have an infinitely long list of real numbers. What can we do with it? One thing that we might be interested in asking is, does this list of numbers converge? Does it kind of settle down to the point where it basically more or less just starts repeating the same number, or does it just keep bouncing all over the place? So what do we mean by convergence of a sequence? Well, we can write out a definition like this. We can say the sequence an has limit L, a real number, which we could also denote by saying limit n goes to infinity of an equals L, a real number, or even more simply, just an goes to L, a real number. These all mean the same thing. But we'd say the sequence an has limit L, a real number, if and only if, this I with two F's means if and only if, we can make the following statement that, and that we're being a little hand wavy here. We're not going through super precise definitions of limits with epsilons and deltas, but an has limit L, a real number, if and only if the elements an can be made as close as you like to the proposed limit L by restricting n greater than or equal to k for some k. Note that this isn't quite the same as saying that you keep getting close to L as you go further in the sequence. So if we thought of graphing our sequence, that's something we can do, right? We could just say this is like the n axis, and here we have 1 and 2 and 3 and 4 and so on, and these are our outputs an. So if I have something like this, maybe this is like e to the negative n cosine of n, something like that. Well, I see that if I have a hypothetical limit L, I think it's probably going to be 0. If I say, okay, I want you to be within a certain distance of L, and I want you to guarantee that you're within that distance of L by picking a certain n to start at. But once you pick such an n to start at, say in this case n equals 3, you have to stay in this corridor. You have to stay this close to L from that point forward. If I demand that you stay closer to L, you should be able to satisfy that by picking a larger value for n and then stay that close to L or closer for that from that point forward. If I have a situation where I do something like, I'm up here, and then it's 0, and then here, and then it's 0, and then here, and then it's 0. And I thought that my limit was, if I thought my limit was 0, well, I can always find, no matter how far out I am in the sequence, a number that's within, some small corridor of L equals 0. But I can always also find another number that's outside of that corridor. This limit would not exist. So something like a sinusoid, that limit's not going to exist. That sequence is not going to converge. So we need to be able to say that if I tell you how small of a corridor I want around L, around your proposed limit, you can go far enough in the sequence that from that point forward, all of the numbers are within that corridor of L, that small corridor. If I make the corridor smaller, you can still satisfy that constraint by going a little further out into the sequence. Okay, so we have a really helpful theorem. We know an awful lot about limits of real-to-real functions. So here, let's say we have a function f taking a real input and giving a real output. Can I leverage all that I know about limits of real functions? Can I leverage that to help me figure out limits of sequences and convergence properties of sequences? And I can say the following. I can say that if I know that limit as x goes to infinity, f of x, where f is taking real inputs, equals L, a real number, or it could be plus or minus infinity, but for now, let's just think of it as a real number. And also, if an is f of n, for n in the domain of an, and basically a natural number, then I could say that the sequence also goes to L. So if the limit of a function is L, and this we get the sequence by plucking numbers out of the function, then the limit of the sequence is also L. This makes a lot of sense, right? If, let's say this is my proposed L for, say, this function. So this function, in some sense, has a lot of points on the curve. The further I go to the right, this is limit x goes to infinity. The further I go to the right, the closer every one of the points on F gets to L. If I get my sequence by just plucking a point here and a point there off of this curve, if all of the points on f of x get closer and closer to L and satisfy this limit condition, then certainly the kind of sample points, in a sense, the points here and there that I pluck off of f, certainly they get closer and closer to L as well. It's very important to note that the inverse and the converse are not true. So for instance, so this would be an example where the theorem holds. But if I try to ask, okay, is it true that if f of x does not converge, and if f of n equals an, does that mean that an doesn't converge either? And that's not true. Let's take, for example, a sinusoidal. So like a cosine function. So if I look at this f of x, if I take its limit as x goes to infinity, of course, doesn't exist. It just keeps going up and down between minus and plus 1 forever. But what if I took a sequence? What if I chose points off of here that were like at this peak? That's the first one. And at this peak for the next one. And at this peak for the next one. What is my sequence? It's just 1, 1, 1, 1, and so on. Of course, this converges to the limit L. If my real function does not converge, if the limit doesn't exist, my sequence that's generated from that real function might or might not converge. Its limit might or might not exist. It depends on how the sampling from the real function is working. But if the real function does converge to a limit, then every point in that real function kind of satisfies that criterion. And then certainly the ones that we pluck out, regardless of how we choose to pluck them out, are going to satisfy the limit criterion because every point does. Okay. And then similarly, if sequence an converges, like maybe it does here, maybe this is gotten by some sinusoidal, if it converges and it was generated by some cosine type function, that says nothing about what happens in the real valued case. Does cosine of x converge, or cosine of whatever it might be, 2 pi plus what, like or pi over 2 plus 2 pi n all times x or something like that. Does that or pi over 2 plus 2 pi x, does that converge? Cosine of that, does that converge in the real side of things? Certainly not. Okay, so we have this theorem that we're going to make use of here. We also have some nice properties for limits of sequences. If we have two sequences that are convergent, an and bn, and if c is a constant, it's a real number, then we can say the following. The limit splits sums apart, just like it did for real functions. Constants can come out of limits, just like before. The limit of the product is the product of limits, also just like before, again, presuming that the resulting limits exist. The limit of the quotient is the quotient of the limits, just like before, again, assuming that each of the individual limits exists and that this limit Vn is not zero. And limit of something to a power, the power can come outside of the limit. So let's look at an example. This is going to be an example that we'll build off of throughout the course. Very important example. We'll see it pop back up in a different way in 11.2 and actually be used throughout chapter 11. Okay, example, for what values of R is the sequence R to the N convergent? So here R is a real number. For what real numbers is R to the N convergent? Note that N is the index here. So what does the sequence R to the N equals 1 to infinity look like? It looks like R to the 1 or R squared, R cubed, and so on. So I get each next output by multiplying the previous output by R. Well, let me look at some special cases. Maybe, what about R equals 0? This yields the sequence 0, 0, 0, etc. Of course, this converges. Let me be careful with my random use of arrows there, because I want to use arrows specifically here. So for the R equals 0 case, we get the sequence 0, 0, 0, etc. This, of course, converges to 0, a real number. It's convergent. Looks good. What about the R equals 1 case? 1, 1, 1, so on. This clearly converges to 1. That converges. What about something like R equals 1/2? We have 1/2, 1/4, 1/8, 1/16, 1/32, and so on. We see that this sequence converges to 0. Like, no matter how close I want you to get to 0, you can go far enough out, and all of the elements of the sequence from that point on will be within that interval of 0. Right? These just keep getting closer and closer to 0. This sequence converges. R equals 1/2. What about a negative number for R? And we're just going through several special cases here, just looking at lots of examples to get a feel for this, by the way. Like, we're not trying to solve, we're not going to go through all of the infinitely many R's. Okay, what's R to the first is negative 1/2. R to the second is plus 1/4. R cubed is minus 1/8. Plus 1/16, and so on. We are oscillating back and forth here, but we're oscillating back and forth while our magnitude is getting smaller and smaller. This also goes to 0. This example is, I think I erased it, but this example looks like this. Right. No matter how small the corridor is, you can go far enough out to where if you're going a bit above and below the hypothesized limit of 0, you can stay within that corridor forever if you go far enough out, no matter how small that corridor is. Well, we did R equals 1 above. What about R equals -1? r to the first is -1, r squared is +1, -1, +1, etc. We have our first case where we don't converge. We say this diverges. So when an goes to a limit that's a real number, we say an converges. Otherwise, we say it diverges. Similar semantics to our improper integrals that we've talked about before. So r equals -1 diverges because it just keeps bouncing back and forth. Our outputs are always 1 unit away from, let's say, a hypothetical limit of maybe 0 or something like that. So if I thought maybe L was 0, we're always going to be 1 limit away, or 1 unit away, no matter how far out to the right we go. Maybe I could pick L a little better. Maybe if I pick L equals 1, does that help? Well, no, because now sometimes we're right on the limit, but anytime that we're right on that limit of 1, our next element of the sequence is always 2 units away. So if I said, I want you to stay within a corridor of 1/2 above or 1/2 of a unit below the limit, you could never do it for more than one element, no matter how far out in the sequence you go. So this diverges. What about something like r equals 2, 2, 4, 8, 16? This goes to infinity. Remember, we say that sequence an converges if an goes to a limit that's a real number. Going to infinity, we diverge. We could see a similar thing with, say, r equals -2, -2, +4, -8, +16. This actually doesn't go to infinity. It doesn't go to negative infinity. It keeps bouncing back and forth between positive and negative, and gets larger and larger in magnitude. This limit does not exist. Maybe I'll be a little clearer up here. This limit does not exist also. So in these cases, we diverge. 2 ways we can diverge. The limit could fail to exist, in which case we diverge, or the limit could exist but be plus or minus infinity, not a real number. We diverge there as well. All right, I think I have a pretty good feeling about what's going on here. So what do we see? We have from our theorem, if, what would it be? R to the x converges, then r to the n converges. So what kind of power functions converge? What kind of, as converging mean limit as x goes to infinity in that sense? Well, this is when r is strictly between -1 and then including +1. So we know that all of these ought to converge. And then I know if r is less than -1 or r is bigger than +1, the absolute value of r to the n goes to infinity, with n says that we diverge. And then the only one case left is if r equals -1, sequence of r to the n is -1, +1, and so on, diverges. So we converge if and only if R is in the half open interval, open -1 to close +1. Any questions so far? All right, let's work through some examples and just go through each of these and determine whether they converge or diverge, these sequences. All right, so here I have an equals 3 plus 5n squared over n plus n squared. And looking at this, I see that as n gets large, the numerator goes to infinity, but so does the denominator. A little hard to tell what's going to happen here. But maybe one thing I can do, I remember this trick from real number limits. If I divide top and bottom by the biggest power of n, divide by n squared, and now what happens as n goes to infinity? As n gets larger and larger, I can use my limit laws up here, right? Limit of the quotients, the quotient of the limits, limit of the sums, the sum of the limits, and so on. And I know that 3 over n squared and 1 over n are going to go to 0 as n gets bigger, leaving me with just 5 over 1 or 5. This, of course, is a real number, so the sequence converges. What about an equals n over 1 plus root n? So here again, maybe I look at this and I say, well, numerator and denominator both still go to infinity. I'm not 100% sure. If I maybe divide top and bottom by root n, something like this, I note that my denominator, this bit goes to 0, my denominator goes to 1, but my numerator still goes to infinity. As I let n get larger, that numerator is going to continue to get larger. This goes to infinity. This is divergent. I couldn't use the theorem here about what happens to x over 1 plus root x because that would diverge. Remember my theorem, if I erase all of my scribblings off of it, my theorem says if limit x goes to infinity, f of x equals L, a real number, then this holds. If limit x goes to infinity, f of x doesn't exist or is plus or minus infinity, then I'm not so sure, right? And I suppose I could expand this to where it equals, so I originally stated as L a real number. I could expand it to L equals plus or minus infinity. If this limit was plus infinity, then these ANs would have to go to plus infinity, and same with minus infinity. So I suppose in this case, I actually could have used that in the revised or expanded version of that theorem. But the way that I originally stated it, where I was just looking at real numbers, real limits, real numbered limits, I wouldn't have been able to technically apply it here. If I wanted to expand it a bit, maybe I could make use of that theorem. But I think this was easy enough without trying to expand the theorem and really force the issue. Okay, what about this example down here? I have an equals e to the n plus e to the negative n over e to the 2n plus 1. So maybe I'll start by dividing through by e to the 2n. That's the highest power of e that I see. If I divide through it on the bottom, I get 1 plus e to the negative 2n. And on the top, I get e to the negative n plus e to the negative 3n. The limit of the quotient is the quotient of the limits. And the limit of the sum is the sum of the limits. And I see that all of these e to the negative 1, 2, or 3n, those limits all go to 0, or those functions all go to 0. Those limits are all 0. Gives me 0 over 1 or 0. What about an equals cosine of n? This one's actually quite difficult. It's cosine of 1, cosine of 2, etc. We might have kind of a gut feeling that if we consider f of x equals cosine of x, because we don't have a nice like pi related periodicity here, our inputs are just going from 1 to 2 to 3 to 4. They're not going from things related to pi to other things related to pi. We might guess, and we would guess correctly, that we're just kind of randomly essentially plucking points off of the cosine curve, and that this will never converge, that this behaves more like the real function cosine of x than like one of those special cases where you specifically pluck certain points off of the cosine function that end up giving a convergent sequence. And that's actually the case here. This diverges. It's quite difficult to show that, though. It's not easy to show that, no matter what corridor you put around, say, a limit maybe L equals 0, how can you be sure that you'll always end up happening to pluck a point from, say, higher up on one of the peaks or lower down on one of the valleys, no matter how far out you go in the sequence, right? It's not an easy argument to make, but maybe we'll say based on gut feeling, it seems like this should diverge, and it actually does. So this is the only one of these that's really hand wavy, but I just wanted to show you this example. However, if I have something like an equals cos of n over n, this is like 1 over n times cos of n. And here I see that cosine is stuck between negative 1 and 1, and I have an n on the bottom. So as n gets large, my denominator gets large, my numerator stays small in magnitude, my whole fraction is going to go to 0. This converges to 0. And I suppose I should have said converges here as well. What about something like cosine of 2 pi n? So my sequence now looks like, or sequence an looks like cos of 2 pi, cos of 4 pi, cos of 6 pi, and so on. I'm just, for my sequence, plucking all of these peaks off of here. This actually just looks like 1, 1, 1, and so on. the limit of this sequence is 1, it converges. So we do have to be quite careful with these oscillatory functions like this, right? Sometimes they converge and sometimes diverge when we're in the sequence world. In the real valued world, this one would converge, this limited infinity would exist, this one would not, this one would not. So we have an example of kind of diverges, an example of converges, an example of converges, diverges. So I'm using the term diverges fairly loosely when I'm talking about the real function. Okay, so what about this example? Well, again, from before, we realized that cos of 2 pi n, where n is a natural number, is always just 1. So we can do a bit of simplification first. 1 plus n over n. And we could do a bit more simplification, dividing top and bottom by n. And again, the limit of the quotient is the quotient of the limits. The limit of the sum is the sum of the limits. This 1 over n bit goes to 0 as n gets bigger and bigger. This limit's going to turn out to be 1. Any questions on anything so far? Okay, so I think for the last few minutes here, I think we can get through this problem. Let's take a look at this one. An equals square root of n plus 1 minus square root of n. So what can we do with this? We can't immediately do anything really algebraic, I suppose, with it. We can't we certainly don't want to say this is root n plus 1 minus n or something like that. So what could we do? Well, again, if we remember back to Calc 1, we've seen limits kind of like this before. We've seen some derivatives like this before. We know multiplying by the conjugate sometimes helped. So let's try that here. In the numerator, I have a difference of 2 squares. So I get n plus 1 plus the product of the two different roots minus that same product. Those go away. And then I have minus root n times root n is n over my denominator. Let me simplify a little bit. N minus n goes away. I get 1 over root n plus 1 plus root n. I get something pretty similar to what I started with, but it's in the bottom now. But there's one other really important note. As n goes to infinity, this goes to something like infinity minus infinity. That's an indeterminate form. That could be plus infinity, it could be minus infinity, it could be something in between. It's an indeterminate form, infinity minus infinity. But here in my denominator, I have an infinity plus infinity. Well, that's just infinity. Right? If I have a large positive number plus another large positive number, I get an even larger positive number. Where if I have a large positive number minus another large positive number, I don't know what I have. I might have a large negative, I might have a large positive, I might have something close to 0. But if I add 2 large positives, I get a large positive, no questions there, no ambiguity. 1 over a number that's getting larger and larger, not equals, goes to 0. this sequence converges, and it converges to 0. So the difference between square roots of successive integers goes to 0 as the integers get larger and larger. Any questions on anything so far? Okay, so these next topics, the squeeze theorem, monotone sequence convergence theorem, and so on, well, I haven't decided if I'm going to cover this monotone sequence convergence theorem next class or in the supplement. We'll definitely discuss the squeeze theorem next time, and then we might jump ahead. We might move on to section 11.2, leave a bit of section 11.1 for the supplement, or we might finish 11.1, start 11.2, and then leave 11.2 for the supplement. So I'm just going to look ahead and think, what can we get through next time? What would be a reasonable length supplement, and go from there. But if you want to read ahead, read through 11.1 and 11.2, and then keep an eye out for the supplements on the last bit of chapter 10 and this first bit of chapter 11. Okay, let me stop the recording.